Yeah, well, I'm sorry, this is a fake. I'm in an experimental session, but of course, I certainly can't do experiments, so all I can do is talk about them. So in 79, we held a symposium at the Institute for Advanced Study to celebrate the 100th birthday of Einstein. Unfortunately, Einstein could not be there, but John Wheeler made up for his absence. Wheeler gave a marvelous talk with the title Beyond the Black Hole, sketching with poetic prose and Wheelerian pictures his grand design for the future of science. Wheeler's philosophy of science is much more truly relativistic than Einstein's. Wheeler would make all physical law dependent on the participation of observers. He has us creating physical laws by our existence. This is a radical departure from the objective reality in which Einstein believed so firmly. The subject of this lecture is a couple of thought experiments that are intended to set limits to the scope of quantum mechanics. Each of the experiments explores a situation where the hypothesis that quantum mechanics can describe everything that happens leads to an absurdity. The conclusion I draw from these examples is that quantum mechanics cannot be a complete description of nature. This conclusion is, of course, controversial. I don't expect everyone to agree, or even a majority. The purpose of giving such a talk on a controversial subject is not to compel agreement, but to provoke argument. I've not studied the literature carefully, and I'll not be surprised if these experiments have been published before. If anyone in the audience has seen them before, please let me know, and I'll be glad to give credit to whoever thought of them first. There are two main schools of thought about the meaning of quantum mechanics, which I call broad and strict, using the words in the way they're used in constitutional law, where the broad school says the American Constitution can be interpreted to cover all kinds of situations, and the strict school says the Constitution means just what it says and nothing more. The broad school says that quantum mechanics applies to all physical processes, while the strict school says that quantum mechanics covers only a small part of physics, namely the part dealing with events on a local scale. The extreme exponent of the broad view is Stephen Hawking, who is trying to create a theory of quantum cosmology with a wave function for the whole universe. The historic exponent of the strict view was Niels Bohr, who maintained that quantum mechanics can only describe processes occurring within a larger framework that's defined classically. Against the dualistic philosophy of Bohr, putting strict limits to the scope of quantum mechanics, the quantum cosmologists take a hard line. They say the quantum picture must include everything and explain everything. In particular, the classical picture must be built out of the quantum picture by decoherence. Decoherence is the elimination of wave interference effects that are seen in quantum systems but not in classical systems. I quote a few sentences from Bryce DeWitt which explain decoherence from the point of view of the quantum cosmologists with unusual clarity. So here is Bryce DeWitt. I should let him speak for himself, but anyway, I hope he won't mind my quoting him. In the old Copenhagen days, one seldom worried about decoherence. The classical realm existed a priori and was needed as a basis for making sense of quantum mechanics. With the emergence of quantum cosmology, it became important to understand how the classical realm emerges from quantum mechanics. The formalism is able to generate its own interpretation. After some simple mathematics describing how the quantum system first decoheres and afterwards exhibits classical behavior, DeWitt goes on, the above results have the following implications for decoherence. 1. Although complexity, metastability, chaos, thermal baths, and wave packets can only help in driving massive bodies to localized states, it is massiveness and not complexity that is the key to decoherence. 2, given the fact that the elementary particles of matter tend upon cooling to form stable bound states consisting of massive agglomerations, decoherence at the classical level is a natural phenomenon of the quantum cosmos. 3. Given the fact that the interaction described here is a simple scattering interaction and not at all specially designed like a measurement interaction, the universe is likely to display decoherence in almost all states that it may find itself in. 4. An arrow of time has no basic role to play in decoherence. Well, I won't go further into this. I should get on to the experiments. So I'll describe 2 thought experiments, imaginary experiments that could be carried out with real apparatus if anybody found them worth the time. The experiments are almost trivial, and the results of the experiments are clear and simple. They show, in my opinion, that Bohr is right, that limits exist for the scope of quantum descriptions. The first thought experiment, I don't have a picture of that, I only have some equations, but it's easy to imagine. It just consists of 2 small Cherenkov counters separated by a distance with empty space in between. An electron is fired through the first counter at time t1 and hits the second counter at time t2. The positions of the counters and the times of arrival of the electron are measured. First, I give you a simple qualitative argument and then a more careful quantitative argument. The qualitative argument goes like this. Suppose the positions and times are known precisely. Then the velocity of the electron between the counters is also known precisely. If we assume that the mass of the electron is known precisely, the momentum is also known precisely. But this contradicts the uncertainty principle, which says the position and momentum of an electron cannot both be known precisely. The contradiction means that it is not legitimate to use a quantum description to describe the electron moving between the 2 counters. To make the conclusion firm, I give you now a quantitative argument which takes account of the inevitable inaccuracy of the measurements. This argument is just an exercise in elementary quantum mechanics, and the experiment, in fact, is just an old-fashioned 2-slit experiment with the slits arranged in series instead of in parallel. The time interval between the 2 measurements does not need to be measured, at least does not need to be measured accurately. We assume only that the time interval is known to be greater than capital T. Suppose there are 2 parallel slits of width capital L, one placed at the exit from the first counter and the other at the entrance to the second counter. So you have the 2 counters, then the 2 slits in between, and then free space in between. So you can imagine it just as an apparatus about so big. When an electron is counted in both counters, we know that it has passed through both slits. The positions of the slits are measured with sufficient accuracy so that the uncertainty of x as the electron passes through either slit is less than capital L, where x is the coordinate of the electron perpendicular to the plane containing the slits. So if you imagine that the 2 slits are vertically one above the other in this direction, then x is the perpendicular direction, perpendicular to the slits. Well then, so the first equation there is just the definition of the dispersion in the value of this coordinate x. And that's a function of time as the electron travels down between the 2 slits. According to the virial theorem, which holds for an electron traveling freely according to the rules of non-relativistic quantum mechanics, of course it's also true classically as well. So the second derivative of capital D, the second derivative of the dispersion, is twice over m squared times the dispersion in the momentum, where m is the electron mass and delta p is the dispersion in the momentum conjugate to x. The right side of that equation now is independent of time, since the electron is traveling freely between the 2 slits. So you can integrate the equation very simply, and capital D is just equal to the value it has at the minimum plus the delta p squared times the t minus t0 squared over m squared, where t0 is the time at which the dispersion is a minimum, and t is the time you're observing. So it's a simple quadratic dependence on time. And t0, of course, could be anything you like, but clearly it would be convenient to put it somewhere between the upper slit and the lower slit. But the Heisenberg uncertainty principle gives you an upper limit on the dispersion, a lower limit on the dispersion in momentum, which is equation 4, product of capital D with the dispersion in the momentum is greater than or equal to 1/4 h squared. And that, together with the equation 3, the previous equation, see, you have two terms, one of which is proportional to D, and the other term is inversely proportional to capital D. So when you add them up, that has to be at least as it's twice the arithmetic mean of the two terms. It has to be at least as large as twice the geometric mean. And so that gives you equation 5, a very simple inequality for the dispersion. It says that, in fact, that the dispersion is greater than or equal just to h over m times the time interval that the electron has traveled. And that says, in fact, this is, in fact, exactly the Bohm diffusion. If you know, Bohm invented two kinds of diffusion, both of which were important discoveries, one of which applies in plasma physics and the other applies in quantum mechanics. So this is Bohm diffusion in quantum mechanics. If you take the Bohm interpretation of quantum mechanics, then the electron is actually just diffusing by a Brownian motion. And this tells you that the actual diffusion has to be at least as large as the Brownian motion which follows from Bohm's picture of the quantum processes. So it's at least as large as just h over m times the time interval. Well then, since the value of the capital D at either of the counters you know is less than capital L squared, and you know that the value of t minus t0 must be at least as large as half capital T, and if you add up the two intervals above the minimum and below the interval, they add up to capital T. So if you put those two things together, you get the last equation, which just says that twice L squared divided by T is greater than or equal to h over m. So that follows just from quantum mechanics and nothing else. So if the quantum description would apply to that situation, the length and the time have to satisfy that inequality. But in fact, of course, what makes it interesting is that this number on the right-hand side, h over m, is actually quite large. It's it's roughly in CGS units. It's just 1 centimeter squared per second. So it means, in fact, that it's very easy to violate that inequality with reasonable numbers. So I just take for an illustration that if you take the width to be of the order of 1 micron, which is not stretching the state of the art, you can fairly easily make a 1 micron slit. And then, so that's L squared is 10 to minus 8 centimeters squared. So that inequality then says that the bottom line there is violated for any time interval longer than 20 nanoseconds. Well, suppose you have an electron of 1 kilovolt energy, which is quite convenient for doing such an experiment. So it's going at the order of 10 to the 9 centimeters per second. So it means that it goes 20 centimeters in 20 nanoseconds. So the length of the travel only has to be 20 centimeters long to violate that inequality. So you can easily imagine setting up the experiment, say, with a travel time of half a meter. And there must be then a contradiction. Well, just to make the purpose of the experiment clear, I hasten to add, it doesn't prove quantum mechanics wrong. All it says is that quantum mechanics is wrongly applied to that particular situation. Before discussing the meaning of that experiment, I go on to the second experiment. The second experiment, so I have a picture of this one, which I stole from the Einstein philosopher book, which you've probably all seen, the famous Einstein box. A device invented by Einstein for the purpose of violating the uncertainty principle. Einstein wanted to use the box to prove that quantum mechanics was inconsistent. Einstein confronted Bohr with this box at a public meeting in 1930. Bohr won the argument with a dramatic counterattack, pointing out that Einstein had forgotten to take into account his own theory of general relativity when he discussed the behavior of the box. When Bohr included the gravitational effects that follow from general relativity, it turned out that the uncertainty principle was not violated after all. So Einstein was defeated, and the box became a victory trophy for Bohr. The idea of the Einstein box is that you hang it from a spring balance and measure its mass by measuring its weight in a known gravitational field. You measure its weight by measuring the momentum transferred to the balance by the spring in a given time. So little p is the momentum and capital T is the time that you take to measure it. So the uncertainty in the mass is then given by this next equation. Just uncertainty in the mass is just uncertainty in the momentum divided by Newton's constant times time. No, that's not Newton's constant. Little g is the local gravitational field, the local gravitational acceleration. The box has a window with a shutter that can be opened and closed from the inside, and a clock that measures the times when the shutter is opened and closed. It's important that the clock sits inside the box so that the weighing is not disturbed by time signals coming into the box from the outside. At the time when the shutter is open, a photon leaves the box and carries away with it a mass proportional to its energy. The weighing of the box before and after the emission determines the energy of the photon. So then the measured energy of the photon has an uncertainty which is given by equation 8, just c squared times the uncertainty in the mass. And Einstein thought he could violate the uncertainty principle between energy and time, which is equation 9, because he thought he could set the internal clock to make the uncertainty in the time of emission of the photon as small as he pleased. Bohr defeated this scheme by pointing out that the rate of the clock would be affected by the position of the box in the gravitational potential, according to general relativity. If the uncertainty in the position of the box is delta x, then the resulting uncertainty in the clock time during the weighing is given by equation 10. And putting together 8 and 10, you can see the uncertainty relation between energy and time for the photon follows immediately from the uncertainty relation between position and momentum for the box. Point, set, and match to Bohr. So my second thought experiment is nothing more than a repetition of the Einstein box with one measurement added. You arrange a photon detector with an accurate clock outside the box and measure the time at which the photon arrives at the detector on the outside. The uncertainty in the arrival time is then independent of the movement of the box. The uncertainty in the emission time is determined by the uncertainty in the travel time of the photon. The travel time is uncertain according to general relativity because the route of the photon in the gravitational potential is uncertain. However, we can arrange an optical system with f number little f that will focus the photon onto a fixed point at a distance little l, which is f times little x, f times delta x. So here's the last. From the window, no matter where the box happens to be. The travel time of the photon from the window to the focus will then be little l over c, with an uncertainty introduced by the gravitational potential as before. The travel of the photon from the focus to the detector is along a known path and introduces no additional uncertainty. So then the travel time uncertainty is given by 12, and that together with the equation 8, which I won't bother to put up again, it gives you finally the product of the uncertainty in energy and time is now given by this last equation, which is quadratic in the uncertainty in position. So you can now choose the delta x to be as small as you like. So the uncertainty relation between energy and time will be violated, even though the relation between delta x and delta p is satisfied. So in this way, we can achieve the violation that Einstein intended when he introduced his box. And in the second experiment, like the first, the violation is easily achieved with apparatus of desktop size. After 70 years, Einstein is finally vindicated. Of course, Bohr would not have been disturbed for a moment by those two thought experiments. Both of them only violate the uncertainty principle by violating the rules that Bohr laid down for a legitimate use of quantum mechanics. Bohr's rules say that a quantum description can only be used to predict the probabilities of different outcomes of an experiment, not to describe what actually happened after the experiment is finished. These thought experiments merely confirm that that restriction in the use of quantum mechanics is necessary. If, in the first experiment, it were possible to define a wave function for the electron traveling between the two counters, this wave function could be proved to satisfy the uncertainty principle by the usual mathematical argument. But we saw the uncertainty principle is violated, and therefore no such wave function can exist. Perhaps Einstein would be happy to learn that his box is still alive and well after 70 years, and still making trouble for believers in quantum mechanics. So let me summarize the conclusions. I have two general conclusions. First, statements about the past cannot in general be made in quantum mechanical language. For example, we can describe a uranium nucleus by a wave function including an outgoing alpha particle which determines the probability that the nucleus will decay tomorrow. But we cannot describe by means of a wave function the statement, this nucleus decayed yesterday at 9 o'clock in the morning. As a general rule, knowledge about the past can only be expressed in classical terms. Lawrence Bragg, a shrewd observer of the birth of quantum mechanics, summed up the situation in a few words. Everything in the future is a wave. Everything in the past is a particle. Second conclusion, the role of the observer in quantum mechanics is not to cause an abrupt reduction of the wave packet, with the state of the system jumping discontinuously at the instant when it's observed. The picture of the observer interrupting the course of natural events is unnecessary and misleading. What really happens is that the quantum description of an event ceases to be meaningful as the observer changes the point of reference from before the event to after it. We don't need a human observer to make quantum mechanics work. All we need is a point of reference to separate the past from the future, to separate what has happened from what may happen, to separate facts from probabilities. Thank you.
Yes, question.
Since you're a card-carrying theorist, what happens when you do the Cherenkov calculation by conventional quantum mechanics? It's a very straightforward problem. It's like a sequential ionization. How does the calculation fail?
Well, that part of the calculation was done by Heisenberg. And of course, the whole point is that the quantum mechanics cannot be applied consistently to that situation.
Of course it can. It's a very straightforward problem. It's a double ionization, sequential ionization of two atoms by a fast electron.
No, but
it's a freshman quantum mechanics calculation.
The point is, if you have any wave function going through the first slit, it will scatter all over the place. most of it won't get through the second slit. That's what happens. So that you can't describe with the wave function the statement that the electron actually went through the second slit. All you can do is say there was a probability that that would happen after it went through the first slit. That's okay, because you're then only talking about the future as seen from the first slit. But as soon as you say it actually went through the second slit, then quantum mechanics doesn't work. And what happens in the Cherenkov counters doesn't make any difference. I mean, that part of the calculation you can do. But I'm only concerned with what happens between the two slits.
All right, up here.
Bill Unruh, way out back here. I just wanted to point out that this whole business of measuring the time, for example, the time of flight or even the time of occurrence of something, is something that a former student of mine and I have looked at, Jonathan Oppenheim, who's here, so he might make further comments on that. The other thing is that the time-energy uncertainty relationship has a long history of being badly formulated, and already in the 1950s, I believe it was, Aharonov and Bohm pointed out that you can measure the energy of something in an arbitrary accuracy in an arbitrary short time. That's not the meaning of the time-energy uncertainty relationship. The weighing of the box is a much closer thing for that. Third point is also something that Aharonov has pointed out, and other people as well, and that is that if one imposes conditions both in the past and the future, which is perfectly possible to do, and we do that all the time in experiments, then it's certainly true that in the intermediate time, quantum mechanics applies perfectly well. There is, of course, no wave function which describes a situation there, which is most clearly illustrated by the fact that you can set situations up where both Sx and Sy are perfectly are exactly defined for a spin 1/2 particle at an intermediate time, even though Sx plus Sy is not perfectly well defined. So I guess all three of your points have a previous history that various people have looked at.
Good. Yes, well, I'm profoundly ignorant of the history, so I'm very glad to be educated. Thank you very much. Yes.
Other questions? Yes.
Can you hear me?
Yes.
I would be very interested to hear your opinion on what kinds of conceptual insight one can gain from David Bohm's quantum potential interpretation, and whether that's really been fully exploited.
Yes, well, I happen to have had terrible arguments with Bohm while he was formulating this version of quantum mechanics. In fact, he and I were having supper together every day in Princeton, and I fought bitterly against him at that point. I mean, he's a good friend, but I don't like his interpretation. And it always seemed to me it sort of missed the point. So I'm not really the right person to answer that question. I love quantum mechanics the way it is, and I don't find that Bohm's picture adds anything useful as far as I'm concerned. Yes.
Question here.
I'm sorry.
This is the next one. We'll come back.
Okay.
Yeah, it turns out that a different version of the first experiment has been done, and that does work, and that's if you look at a passage of a neutron through a neutron interferometer, you can get a very accurate measurement of the delta V and the delta X through it. And Professor Scholl, before he died, did very accurate measurements. There's a phenomenon when at the edge of just barely going through the interferometer, you have a phenomenon called pendulosing, where you can check to see exactly how coherent the neutron is, and he saw something like 300,000 fringes or so, from which you can calculate the delta X and the delta P. The wave packet holds together for something like about 100 times the length of the neutron interferometer before it sort of becomes incoherent. But the formula is very close to yours, and they work very well in practice.
Good. Yes, I'd like to see that. Of course, the quantum mechanics describes everything beautifully if you do it right. It's only just that there are ways of not doing it right.
Yes.
Yes. Casey Blood is my name. When you have the uncertainty principle, it says the expectation value of delta x squared times the expectation value of delta p squared is greater than or equal to h bar squared over 4. When you have expectation values, it seems like to find a violation, you would have to make measurements on many electrons, not just one. Is that correct?
No, that is not true. The expectation value applies to a single electron, and it's, you know when it goes through the slit that its value of x is in that particular interval. So you have a sharp limit on the value of x, so that the expectation value of x squared cannot be as large as L squared. In fact, I've given up a factor of 2 there just because I didn't need it. But you have an absolute limit.
But if you repeated the experiment, the momentum would be different each time. And it's the spread in that difference, is it not?
Maybe the question is, if you try to measure the spread, then you have to use many electrons, many individuals.
That may be true, yes. Of course, I'm not measuring it. I'm simply I'm saying this wave function is a mathematical absurdity, but that has nothing, that's really nothing to do with what one might be able to measure.
One more question up here.
Yes, Lee Smolin. I want to say bravo, and I had earlier criticized the other approaches to quantum mechanics because they wouldn't extend to cosmology. What we need to be able to do meaningful quantum cosmology, like we'll hear people attempting to do tomorrow, is an interpretation, a viewpoint on quantum mechanics that can be consistently applied not by some idealized observer outside the universe, but by a real observer inside the space-time. And what you've said is sensible and is the first things that we've heard in the symposium, which I think could be the start of a good formulation of quantum cosmology. And there are other people who are indeed making new kinds of formulations of quantum cosmology which realize these kinds of ideas where the observer is inside the universe, and we'll hear more about them tomorrow.
Good. Thank you very much.
Well, thank you very much, Freeman.
But to provoke arguments. I've not studied the literature carefully, and I'll not be surprised if these experiments have been published before. If anyone in the audience has seen them before, please let me know, and I'll be glad to give credit to whoever thought of them first. There are two main schools of thought about the meaning of quantum mechanics, which I call broad and strict, using the words in the way they're used in constitutional law, where the broad school says the American Constitution can be interpreted to cover all kinds of situations, and the strict school says the Constitution means just what it says and nothing more. The broad school says that quantum mechanics applies to all physical processes, while the strict school says that quantum mechanics covers only a small part of the elimination of wave interference effects that are seen in quantum systems but not in classical systems. I quote a few sentences from Bryce DeWitt which explain decoherence from the point of view of the quantum cosmologists with unusual clarity. So here is Bryce DeWitt. I should let him speak for himself, but anyway, I hope he won't mind my quoting him. In the old Copenhagen days, one seldom worried about decoherence. The classical realm existed a priori and was needed as a basis for making sense of quantum mechanics. With the emergence of quantum cosmology, it became important to understand how the classical realm emerges from quantum mechanics. The formalism is able to generate its own interpretation. Yeah, well, I'm sorry, this is a fake. I'm in an experimental session, but of course, I certainly can't do experiments, so all I can do is talk about them. So in 79, we held a symposium at the Institute for Advanced Study to celebrate the 100th birthday of Einstein. Unfortunately, Einstein could not be there, but John Wheeler made up for his absence. Wheeler gave a marvelous talk with the title Beyond the Black Hole, sketching with poetic prose and Wheelerian pictures his grand design for the future of science. Wheeler's philosophy of science is much more truly relativistic than Einstein's. Wheeler would make all physical law dependent on the participation of observers. He has us creating physical laws by our existence. This is a radical departure from the objective reality in which Einstein believed so firmly. The subject of this lecture is a couple of thought experiments that are intended to set limits to the scope of quantum mechanics. Each of the experiments explores a situation where the hypothesis that quantum mechanics can describe everything that happens leads to an absurdity. The conclusion I draw from these examples is that quantum mechanics cannot be a complete description of nature. This conclusion is, of course, controversial. I don't expect everyone to agree, or even a majority. The purpose of giving such a talk on a controversial subject is not to compel agreement physics, namely the part dealing with events on a local scale. The extreme exponent of the broad view is Stephen Hawking, who is trying to create a theory of quantum cosmology with a wave function for the whole universe. The historic exponent of the strict view was Niels Bohr, who maintained that quantum mechanics can only describe processes occurring within a larger framework that's defined classically. Against the dualistic philosophy of Bohr, putting strict limits to the scope of quantum mechanics, the quantum cosmologists take a hard line. They say the quantum picture must include everything and explain everything. In particular, the classical picture must be built out of the quantum picture by decoherence. Decoherence